Alrighty, back for the fossil record. So we're going to talk a little bit about geological time and some of the history pieces just so you have that as a background. Some of this you guys have already heard. This is not anything new. Some of it is new. So if you look at this image, this is pretty typical when we're talking about something that's fossilized. And some of you guys have seen things like this. This is a scorpion stuck in amber. And we have quite a few of these that you can actually find different places. And obviously, you probably have heard, maybe you don't know, that Jurassic Park, the whole movie behind it was from a mosquito encapsulated in amber that actually held the DNA of dinosaurs, and that's how we got to the point of having that story. Okay, so let's talk fossils. Let's talk the word paleontologist. You guys all hear the word paleontologist, and the first thing that pops in your head is dinosaurs. It's actually paleontologists study fossils. So what's a fossil? Fossil record, in this case, we're talking about information from past life. So that includes, we can talk about structure, we can tell what they ate, we can tell who ate them, talk about environment. So we've talked a little bit about this already, and we said that the fossil record tells us a lot. It also leaves a lot of holes because it can't tell us everything because we don't have a full picture. We only have what is left behind. And we talked about the fact that plants don't really leave fossils because they don't have a lot of hard structure. So there's not tons of plants in the fossil record, just some. So we don't have a full picture. This is one of my favorite statements of all time, and I want you to have this sink in as I read it, and we're going to continue to talk about this as we go. Over 99% of all species that have lived on Earth have become extinct, which means that the species has died out. One more time. Over 99% of all species that have lived on Earth have become extinct. So pause and think about that for a moment. That realistically gives you a moment to think about the fact that we, as a species, would have the ability to become extinct. I know we really think of the Earth in terms of human time. Remember that human time is such a small portion of the full picture. But 99% of all species that have lived on Earth have become extinct. Okay, so how do fossils form? Generally speaking, they're going to form in sedimentary rock. Remember, sedimentary rock is that rock that's going to be made of lots of different pieces pressed together. So some of them are really large and complete. Some of them are really small and they're just little parts. It could be a bone. It could be an imprint of a bone. It could be an imprint of teeth. It could be an imprint of just about anything. Or it could be an entire preserved animal. So we have all of the above when we talk about fossils. So this is kind of showing you what fossil formation would look like. Okay, so this is obviously we're looking at a fish who's actually now died. And we have water that is actually going to carry those small rock particles, excuse me, to going to lakes and seas. And so then we have the issue of where we have that dead organism or it can become buried by layers of sediment, which form that new rock. Over time gets covered and it gets to the point where we actually have pressure on them, creating a situation where the preserved stuff remains inside of that soil, and then it can be discovered later and we actually pull it out of the soil again. So when we have those fossils, what does it really mean to us? Because that's the important part, right? It's not just about the fossil itself, it's about actually being able to use that fossil evidence. So relative dating is the first part, and you guys, we've talked about this already, the fact that realistically we talk about the age of fossils and we talk about where they're located. So we talk about the placement within the fossil into the layers of rock, and within those rock layers we order them in age, from the top being the newest and the bottom and the strata being the oldest. So we go from the newest, and then as we get down it gets older and older and older and older and older as we go. Okay, that makes sense, pretty logical. The one thing that I want to make sure that you guys see is the term on here, which is index fossil. An index fossil is going to be something that's recognizable species that existed for a short period of time, but it was found in a wide geographic range, which means it can be found in lots of places, but for a short window. And that short window becomes important, and the reason the short window is important is because it really set us up so that we can say when it started and when it ended. So we can tell a finite window, and then we can make comparisons around that time frame. Wide geographic range has to be there so that it can be found in many places, and so we have it as a reference point to be able to go off of for all areas, not just for one. Okay, so this is showing you relative dating, and we can look at those rock layers. And as we look at those rock layers, we can actually make some extrapolations. If you're taking a look, you can see where they have similarities and where they have rock layers that are the same, or finding things that are the same. So you can actually see here we've got a trilobite that you're able to find in the same layers, but they're not found in the same spot because we don't have as much sediment on top here as we do here, and we don't have as many layers listed below as we do here. Okay, we have a nautilus that you can find as well. So you can see those in the same layers. So really are looking at the idea that these layers are the same, or we have materials, we have fossils that are left behind to be able to help us find that relative dating. Radioactive data, on the other hand, is going to be something of a finite number, so we're actually looking at using radioactive material to determine the actual age of something. We do this through what's called half-life, through radioactive dating. And really what we're talking about, those of you guys who've done this in math already know that when we're talking about a half-life, we're talking about the length of time that's required for half of the atoms in that sample to decay. Basically, we have an amount, and how much time does it take us to get to half of that amount? And in this case, we're actually looking at the radioactive atoms, and that allows for us to be able to look at that sample and figure out the actual age. So now we use radioactive decay to actually to give an absolute age to rocks, meaning this is how we figure out how old things really are. So now some of the elements are radioactive, and they break down into non-radioactive elements, and that becomes an important factor when we're looking at radioactive dating. So this is showing you what it looks like if we're using potassium-40, which is a radioactive atom that we're working with, and it shows you how we get to the point of finishing and figuring out how long something has been in existence by how much of that potassium-40 exists. Most common for us is really to look at carbon-14. We use carbon-14 as our dating. Part of the reason is because most organisms that we're talking about are carbon-based life forms, and carbon-12 is not radioactive and does not decay. So therefore, when we start with carbon-14, that does exist within carbon-based life forms as well. And it does begin to decay as soon as the organism dies. So when we look at that and we can compare the amount of carbon-14 and the amount of carbon-12 in a fossil, we can actually determine how long the organism lived and when they lived. This is actually the most common when it comes to organisms, and we're not talking about for rock, but when we are talking about for organisms, this is what we actually look to see how much of our carbon-14 and carbon-12 are left within that organism to determine the absolute age of it. Okay, so we start talking about time scale in addition, so we can kind of figure out time frames when we're looking at this. Geological time starts with the Precambrian period, and this covers about 88% of the Earth's timeline. A little bit more, might be a little bit closer to the 89% now, but about 88%. We will talk about the fact that it's broken into era and periods. So when we talk about this, we're talking about your Precambrian time period, and you can see the time scale in which it was and how many millions of years ago. So we really take our Precambrian time and we actually take that and break it into three eras: the Paleozoic, Mesozoic, and Cenozoic. Those three eras is our big chunk, and then we can actually break those eras into smaller groups, which are called periods. And those ranges, those periods range from tens of million years to less than 2 million years. These are usually named for locations where the rocks and fossils were actually discovered. You'll actually see some of those as we look through this. So we have in our Paleozoic period time era, we have Permian period, Carboniferous, Devonian, Silurian, Ordovician, Cambrian. We also have our Mesozoic, which you guys probably have heard of more commonly, Cretaceous, Jurassic, and Triassic. And the ones that most people know are Jurassic and Triassic because those are the two time periods where we really start to see the exploration of the dinosaurs becoming large and the dominant grouping on the land masses at the time. Cenozoic or Cenozoic is the current time period, and we have the Tertiary time period and we have the Quaternary time period, which the Quaternary is where we are presently, and we have been there for sorry guys, 1.8 million years, approximately. Okay, so these kind of just break down our time periods for us, and that is going to be the info that you need from this.